Okay folks, today we're going to start by looking, let me just put myself in that corner. Okay, today we're going to start looking at graph theory. Very, very exciting mathematics. It's brand new mathematics. Okay, so in the time of Euler, you might have heard of Euler. In the town of Königsberg in Prussia, there was a river with two islands on it. The islands were connected by various beautiful bridges, and people wanted to find out whether you can walk across these islands and cross every bridge once and once only. So you don't repeat any journeys over a bridge. Now that was a question that interested Euler quite a lot. He became super famous for this branch of mathematics, which we'll call graph theory. Okay, so he lived in the 1700s, it says there. He's a super famous mathematician, Leonhard Euler. The question, as it says there, is it possible to cross each one of these bridges once and once only? And that is what we're trying to find out. But before we start our journey there, let us look at a bit of knowledge that you need to know on how you draw equivalent graphs, what a graph is, what a graph consists of. It's fabulous maths. Okay, let's see what the book says. Pictures like the dot and line drawings are what we're going to call graphs. So what they did is they represented that Königsberg bridges problem with a graph that looks like this. Okay, so that is what this rule or definition is referring to. We have, this is what we're going to call a graph. This particular graph over here has 4 vertices, and it has 1, 2, 3, 4, 5, 6 edges. So these are called 4 vertices. Vertex is the singular for vertices, and vertices obviously is the plural. So there are then 6 edges that connect all those vertices on the graph. Now folks, we're going to talk about adjacency in our language that we're going to use for graphs. So this is a graph, by the way. So these 2 vertices are adjacent because they are connected by the same edge. That edge over there connects those 2. These are adjacent. They're connected with 2 edges. Okay? And these are adjacent. They connected with 2 edges. Those 2 far out ones are not adjacent. These are not adjacent. So if 2 vertices are connected by an edge, we say those vertices are indeed. Okay. Now let's see how I can represent a situation as a graph. I'm going to look at this example, and we're not going to look at the solution. Then we're going to try and do our own thing. It says Al, Bob, Cam, Dan and Euler are all neighbors in a social network website on Facebook. The site allows members to be friends with one another. It turns out that Al and Cam are friends. So before we forget this, let's write down. The friend pairs is Al and Cam. Okay? As are Bob and Dan. So Bob and Dan are also friends. Euler is friends with everyone. So all of these are friends with Euler. Okay? So those are also friends with Euler. They're friends with one another, and they're friends with Euler. So let us represent this specific thing on a graph. Draw a graph that represents it. First of all, L, let's call LA, and Cam are friends. So we're going to connect them with an edge. They both are friends with Euler. So both of these are friends with Euler. So there's an edge connecting L with Euler and Cam with Euler. Bob is not friends with L, Dan is not friends with Cam. Okay, but they both are friends with Euler, so we can extend the graph any way we want to, as long as Bob and Dan are not connected to L and Cam. The only connection to L and Cam is through Euler, because Euler is a friend of all three. So how many vertices did we need? We need 1, 2, 3, 4, 5 vertices, and we needed 1, 2, 3, 4, 5, 6 edges to connect those vertices with. So this is one representation of such a graph. We could have done many other representations if we wanted to. Let's say we could have said that is L and this is what's his name, Cam, and we can have, I'm going down a little bit, we can then have Bob and Dan down here. Bob and Dan, those two are friends, these two are friends, all of them are friends with Euler. So Dan is a friend of Euler, Bob is a friend of Euler, Cam is a friend of Euler, and so is L a friend of Euler. But you'll see that A and C are not connected to B and D in any way. So those are two ways that we could represent that situation with L and Dan. Okay, I'm going to look at our next example. Okay, folks, our next example is on the screen. Well, this example says the following. It says, each of 3 houses must be connected to each of 3 utilities. Okay? Is it possible to do this without any of the utility lines crossing one another? Well, let's see. Let's say there's my 3 houses. So those are the houses. And here we're going to draw the utilities 1, 2, and 3. The condition here is each of the 3 houses must be connected to each of the 3 utilities. Now I'm pretty much sure that you can see if I try and draw these lines or these edges, then house 1 is connected to utility 1, utility 2, and utility 3. Okay, so let's see house 2. We can try and go around and around again and around, and they won't cross each other. So let's try that. Okay, so let's see if I have a pencil here, then we can erase it. We don't need to start a new graph if it doesn't work. So there we go with the first one. There we go with the second one. And we can go that way around with the third one. Nothing cross each other here, which is quite clear. But now look at what we've done. We've taken house number 3 and we've boxed it in with that figure. So something is going to cross here. Okay, so I'm sure if you can join H with utility number 3, but how are you going to go through here without crossing anything to get to utility 2? Okay, so this is not possible. Home 1 joins with all 3 utilities, and home 3 joins with all 3 utilities, and that will be the graph that represents this situation. Okay, sorry, so that brings us to our definitions. Before we start defining things, let's just do the investigation. This investigation is quite exciting. It says the following. Which, if any, of the graphs below are the same? So we're only focusing on that first line. We want to know which of those graphs will be the same. Now let's just think about a way that we can talk about that and discuss whether they are the same. We can look at the number of vertices they have. So 1, 2, 3, 4, 5. This is a vertex set of 5. Let me do it at the bottom here. Vertex set 5. Vertex set contains 5 elements. 1, 2, 3, 4, 5. Oopsie. 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. So that doesn't really help us. So we need to look now at the edges. How many edges are there in each of these graphs? And maybe there's something there that we can say. So far, if we just look at the number of vertices, they all have the same number of vertices. So the edges, 1, 2, 3, 4, 5, 6. Edges, there's 6. 1, 2, 3, 4, 5. Edges, there's 5. 1, 2, 3, 4, 5, 6. Edges, there's 6. 1, 2, 3, 4. 1, 2, 3, 4 edges. That's interesting. There's 4 edges in that graph. Okay? So let's look at it again. There's 1, there's 2, there's 3, there's 4. Perfect. Okay, so here 1, 2, 3, 4 edges. Now here we can see there's a difference somehow. So if we just look at the number of edges and the number of vertices, is it enough? Okay, and the answer to that is definitely not. For these graphs to be the same, their structure has to be the same. Okay, so we're going to look at each edge separately and see each vertex separately rather, and see how many edges there comes from each vertex. So there's 2 vertices here, 2 of them, with 3 edges moving into the vertex or out of the vertex. Then there's 3 other vertices, so together they make up 5, with 2 edges going out of each of the vertices. Okay, so let's look at the next one. There are 1, 2, 3, 4, 5 vertices still, and each vertex has 2 edges, either coming in or going out, or coming in or going out of the edge. Let's have a look over here. There's 1, 2, 3 vertices with 2 edges. So there's 3 vertices with 2 edges. So we're now going into the atomic characteristics of each of these graphs. We're looking at the absolute detail. The devil is in the detail. Then we have 2 more vertices, and those vertices each have 3 edges going either in or out of those edges. Now look at this, where my 2 fingers are. 3 vertices, 2 edges, 3 vertices, 2 edges, 2 vertices, 3 edges, 2 vertices, 3 edges. That looks like those 2 graphs are definitely going to be the same. Now we'll look at that just now, how we can see that they are. So they have the same structure. That we're going to just say S1 for structure 1. Let's go to this graph. This graph has 5 vertices, and each of the vertices have 2 edges. So there's an edge, 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 2 edges. Now look at that. Those 2 are identical. So that's structure 2 that we're going to look at. At that atomic level, we can see that the structures are indeed the same. So it looks like these 2 graphs represent the same situation. The graphs might look different, but they represent the same structure. 5 vertices with 2 edges going from each vertex. Now here we simply have 1, 2, 3 vertices, 3 vertices with 1 edge going either in or out of those vertices, and then we have 1 vertex which has 4 edges, 1, 2, 3, 4. Nothing like any of those. Okay, so let us have a look at how we can see that this is indeed the case. I've drawn our one graph. Now remember, we said our pentagon and the star looks the same. So let's see if we can rearrange. I've done an identical pentagon here. If we can rearrange them so that it forms a star. Okay, so let's take that up. Let's bring this one down here. B, I'm just trying anything now. So there's already a crossing happening. What am I going to do with... there we go. Look at that. Look at that. There's the star. Oh, brilliant. So indeed, we have changed a graph that looked like a pentagon into a graph that is indeed a star, and each of those edges still have of the vertices still have the same edges going out of each vertex. Now that gets us quite excited. Let's look at the second diagram. We said the one where we had looked like a quadrilateral with one of the lines, it's not really a diagonal because this is not a line, this is two line segments that meet at a point O. Okay, so there's two line segments lying over there. Now if I can change it into the other one where the three of them are at the top, this is what happened. The two at the top had 3, and then there was 3 at the bottom, look at that, with 2 vertices going out of them. So indeed, those graphs are identical graphs. Okay, so that tells us a lot. That says to us that our suspicion here was indeed correct, that those two are the same. This is the lone wolf. It's not the same as anything else that we have there. Okay, let's move down here. Here they ask us, are the graphs, okay, the graphs above they say were unlabeled, we're not interested in that. Actually, all the graphs we have seen above are just drawings of graphs. So that represents exactly the same situation as this. That represents an exact situation over here. Those two are identical in structure. Those two are identical in structure. So a graph is really an abstract mathematical object consisting of two sets, the one set being a vertex set and the other set being an edge set, where E is a set of two element subsets of V. Now what he means by that is if you talk about an edge, you talk about an edge as two vertices. So here's the two sets. Okay, for graph 1, we'll have A, B, C, D, and E. A, B, C, D, E, representing the vertex set, a vertex set. Sorry, it's not referring to that graph. So we have a vertex set where there's 5 vertices. Okay? Then there's an edge. This is edge 1, edge 2. So A and B are connected, A and C are connected, A and D are connected, and so forth. So we see that there's 6 edges connecting different vertices with one another. So if we were to draw a graph here, let's just go A, B, C, D, and E. A, B, C, D, and E. And we were to draw this on a graph, then AB is an edge. So there's edge 1. AC is an edge. There's another edge on the graph. AD is an edge, so AD is an edge, those two are connected, and so is AE connected. Sorry, that looks a bit cocky, so there we go. BC is connected, and then DE is connected. So that is a representation of what this edge set and vertex set represents in terms of a graph. So each graph can be written as a set of vertices and a set of edges, and that's how we refer to our graphs. We're going to talk more about that later. Now the same happens here at the bottom. There's another way of saying exactly the same thing, and we can draw that graph if we want to. Okay, so then he says some important things here at the bottom that I just want us to pay attention to, and then we're going to work with the particular graphs in the next page. So before we start studying graphs, we need to agree upon what a graph is. Okay, we've got to have a shared understanding of when we talk about a graph, what is it that we're talking about. Okay? While we almost always think of graphs as pictures, dots connected by lines, this is fairly ambiguous. Do the lines need to be straight? Well, in the geometry class, if you say the word line, a line is a straight geometric object. In the function class, if I talk about a line, I'm talking about something that is indeed straight. Okay, so, yeah. So it could be curved, like you saw in my previous ones. And there could be lines. In fact, all of those were curves. None of them were lines. Why not? They weren't straight. Okay. Does it matter how long the lines are or how large the dots are? Can there be two lines connecting the same pair of dots? We saw it could happen. Can one line connect three dots? Well, we saw that. We had that one vertex where three edges were coming into the vertex. We could have had these three dots here and another dot there, and that dot, yes, can connect these two. So all these properties are indeed true. Okay, sorry, so you didn't really see what I was doing there. Okay, so that's not really that interesting or that important. You can remember that from what we've done. So the way we avoid ambiguities in mathematics is to provide concrete and rigorous definitions. That is what a definition does for you. Van Hille said years ago that before you can define something, you must have worked with it before you can really write a formal definition. Now that's what we did here. We did a few examples. We looked at how that examples, what they do differently, what they have in common. Can I make the one from the other? And we are now ready to define the objects that we're going to work with going forward. Is there a graph with no edges? Well, we haven't seen that. But there could be. We could have a node there. That's an island, and here's a city. And they have not yet built roads that goes to the island. Okay, so that is a node or a vertex all by itself. There's no road connecting them. A real-world example that shows that that can happen. We want our definitions to be precise and unambiguous. Very important. But it also must agree with our intuitions for the objects that we are studying. So we're going to rely on that, folks. That's big in mathematics, is relying on your intuition about something and then finding out, is that something indeed true? Okay, folks, we're ready to now define what a graph is. Let's read what he says. The graph definition. A graph is an ordered pair GVE. Okay, so just like functions, we use the same language in a way to talk about this. We're talking about a coordinate pair for now, consisting of a non-empty set. So a non-empty set of V, which we're going to call the vertices. Okay? So you have to have vertices. What that is indeed saying to you, you have to have some vertices to actually have a graph. You can't just have a graph without having any vertices. And a set E, okay, there's a second set E, which we will call the edges. And those edges are two element subsets of V. Okay, so in a way it's just saying what we saw before, but it's formalizing it now. You can talk about a graph as a coordinate pair set VE. The vertices come first, the vertex set, and after that the edge set. But each of the edges is expressed as a set of vertices. Now let's see what that means. Okay, there's the first thing we talk about. So, here's you can see there's curly brackets, so that's your vertex set, and there's a curly bracket, so your G, V, and this is E. There's your round brackets that represents the notation that we've been introduced to up there. Okay, so you have four vertices, A, B, C, and D. You have one edge AB, then an edge AC, then an edge BC, then BD, and then CD. So this could be a graph that looks as follows. A, B, C, D. Let's just do one. A, B, C, and D. Okay, my pencil's going to shine in the light, so I'm going to go over to the pen. So one edge is AB. there's edge 1. Then we have AC, which is edge 2. Then we have BC, edge 3. Then we have BD, edge 4. And then we have CD. So that's a representation of that graph. That's defined by this vertex set and this edge set, as shown in our definition that we just. Okay, so if we go down the page, folks, then we'll see there are other representations for the very same graph. There we go. Could have been like that with BC crossing in the middle. This is more or less what we had, but we also could have put them adjacent and just connect them with loops and edges that shows the adjacency. So AC is adjacent, AB is adjacent, BD is adjacent, BC is adjacent, CD is adjacent, but AD is not. Okay, if we talk adjacency again. So what does this say? We should be careful about what it means for two graphs to be the same. Now we saw that earlier. We can't just look at the number of vertices and the number of edges. Okay, we saw that in the beginning, and then we went into more detail. Now I don't know what I did with my piece of paper with that information on, but I'm sure you can remember that happened 10 minutes ago. Actually, given our definition, this is easy. Are the vertex sets equal? Are the edges sets equal? We know what it means for sets to be equal, and graphs are nothing but a pair of two special sorts of sets. Okay, then he asks us to look at this example. Okay, so I'm going to bring the example in, but I'm going to cover the answer so that we can talk about this by just looking at what it is that we've got. Okay, it says, are these graphs below equal? Well, let's see. Graph 1 has an edge set of 3 edges. So yes, a vertex set rather. So there's 3 vertices in each one of these graphs. But now let's look at how those vertices are connected. Well, AC is connected. AC is not connected over here. So AC is adjacent here. It's not adjacent in the other graph. Then BC and CB are connected. That's fine. So those two are fine. These two are not fine. Can you see, folks, that if you were to draw those two graphs will definitely not be. Okay, there's our second example. The second example asks the same question. Now, how's this example different from the previous one? Well, first of all, there's a vertex set 1, a vertex set 2, an edge set 1, an edge set 2. Those subscripts are just to say we are working with two different graphs. V1 is defined by ABC, V2 by UVW. So we can't really just say there's adjacency or there's non-adjacency because the vertices are labeled differently. So let's look at graph 1. There's 3 vertices. I'm just going to do this. 1, 2, 3. We're going to call this vertex A, vertex B, vertex C. And then we're going to look at the edges and to see which ones are adjacent. So we've got to see, before we go and do this, let's just talk about what we have to do to see whether the graphs are equal. First of all, they've got to have the same number of vertices. Okay? Secondly, they have to have the same amount of adjacent vertices in each of the diagrams. So let's have a look. AB is joined, AC is joined, and then BC is joined. So that sort of looks like a little triangle. Let's look at graph 2. U, V, W. Is the situation different? Well, UV is connected. Okay. Then UW is connected. And then VW are connected. The two of them are connected. So let's now look overall whether they are equal. Each vertex has 2 edges that comes in and out of the vertex. There's 3 vertices, so definitely these 2 graphs represent the same situation. These 2 graphs are indeed equal to one another. Okay, let me just correct what I just said there. They're not equal. They are congruent in their structure. The 2 graphs are totally different, ABC, UWV, but their structures are the same. Now this type of thing we call isomorphic. Graphs that are isomorphic, it's a definition, remember what we're saying now. Graphs that are isomorphic are graphs that have the same structure. They're not equal. Their structures are equal. Hence we're going to call them isomorphic graphs. Okay folks, so that concludes our first video on graph theory, just introducing you to terminology, to what a graph is, to a few definitions. Our second video will continue with isomorphic as a definition. We're going to talk about bijection and isomorphic graphs. Okay, so make sure to watch. And by the way, this is on my YouTube channel, so if you learned from this video and you liked it, please like it at the bottom. Just go down and press the thumbs up, the like, and subscribe to the channel as well. Okay folks, video 2 is on